Welcome to the first part of 12th lecture. Today we will talk about graph connectivity. Graph connectivity is a basic concept in graph theory. It asks the minimum number of vertices or edges that need to be removed from the graph to make the graph disconnected. So, first I will give the formal definition of vertex connectivity, and then we give the definition of edge connectivity, and then we will study the relationship between the vertex connectivity and edge connectivity. Let me first formally introduce what is vertex connectivity. A graph G is K connected if there does not exist a set of k minus 1 vertices whose removal disconnect the graph. Okay. And so, this is the k connected graph. The vertex connectivity say chi g of G is defined as the largest k such that G is k connected. Okay, now I will give example to illustrate these definitions. Let me take this example. I will take a bipartite graph. And let me take complete bipartite graph. So, this is k 3. Now, you can see that if I just remove this vertex, for example, this graph will not be disconnected, but if I remove these 3 vertices, then the graph become disconnected graph. So, I can say that this graph k 3 is one connected because because there does not exist a set of 0 vertices whose removal disconnect the graph here. I can say the graph k 3 is two connected because there does not exist a set of one vertex whose removal disconnect the graph. For example, if I just remove this vertex, then the graph does not become disconnected. So, it is two connected graph. Well, there does not exist a set of one vertex whose removal disconnect the graph. This K33 is 3 connected, because there does not exist a set of two vertices whose removal disconnect the graph K33, but K33 is not 4 connected. Because there exists a set of 3 vertices whose removal disconnect this graph. So, the graph is not 4 connected. So, it is 3 connected, and 3 is the maximum value of k such that the graph is k connected. So, the vertex connectivity of this graph is 3. So, the vertex connectivity of K33, which is K33, which is equal to 3. Okay. So, this is one way of understanding what is vertex connectivity. There is another parallel definition. First, we give the definition of a vertex cut. A vertex cut of a connected graph G is a set of vertices S whose removal disconnects the graph. Graph G. And the other way of understanding this vertex connectivity in terms of vertex cut is the following. The vertex connectivity chi G is minimum size of a vertex set S belongs to V such that G minus S is disconnected or has only one vertex. So, this is also important mostly for the complete graph. Let me take another example of say K4, it is a complete graph with 4 vertices. Now, here you can see that So, what is the vertex connectivity of this graph? It is not difficult to observe that the vertex connectivity of this graph K complete graph with 4 vertices is equal to 3. So, if you remove 3 vertices, you will be left with only one vertex, that is all, and that is the connectivity of this graph. Okay. And in terms of vertex set, if you want to understand the vertex connectivity here, then your minimum size vertex cut consists of these 3 vertices. If you remove these vertices, the graph will become disconnected. So, either it will become disconnected or it will have only one vertex left. Okay. So, next we talk about the edge connectivity. An edge cut, similarly like vertex cut, an edge cut of a graph G is a set of edges whose removal disconnect the graph. And the edge connectivity K prime G is the size of a smallest edge cut. Okay. So, edge cut is a set of edges whose removal disconnect the graph, and edge connectivity is the size of the smallest edge cut, right. And we usually use the standard notation to denote the edge cut. An edge cut is a set of edges of the form S complement. So, I will explain this one where S is a non-empty proper subset of V, and of course, S complement is V minus S. So, let me again consider the complete graph with 4 vertices. So, this is K 4 and the vertices are A, B, C and D. Now, if I take my S to be say A, and then it is a non-empty subset of the vertex set, and S complement, then obviously is B, C, D. So, the edge cut is consist of these 3 edges. The edge cut here, the S complement. So, S complement here is consist of these 3 edges, this edge, and this edge. Okay. So, S complement is the edges between S and S complement. They are AB, AC and AD. So, these are the edges in the edge cut. Now, you can see that if you remove these 3 edges from the graph, if I remove these three edges from this graph, the graph will become disconnected. So, that is why this is an edge cut. Okay. So, I hope that you understood the definition of edge cut, and here the edge connectivity of K4, you need to remove minimum 3 edges to make this graph disconnected. So, K prime K4 is also equal to 3, and the vertex connectivity was also 3 for this graph. Now, let me take another example to sort of get idea about how this vertex connectivity and the edge connectivity are related. So, I will take this graph. There is no specific name for this graph probably. Look at this graph. Now, the vertex connectivity is the minimum number of vertices that must be removed to make the graph disconnected. So, if I call this graph G VE, then clearly the vertex connectivity Kg is what? Kg is minimum you need to remove one vertex. If you remove this vertex, for example, from this graph, the graph will become disconnected. So, the vertex connectivity is equal to 1, and the edge connectivity K prime G for this graph is 2. You can see that if you remove this edge and this edge, the graph become disconnected. So, the edge connectivity of this graph is 2, and what is the minimum degree of this graph? Delta G is equal to 3. So, what we can see that at least for this specific graph, the vertex connectivity is less than or equal less than the edge connectivity, and the edge connectivity is less than the minimum degree of this graph. Next, we prove a theorem which relates the vertex connectivity, edge connectivity, and the minimum degree of a graph G, and the relation is that the vertex connectivity is always less than or equal to the edge connectivity, and the edge connectivity is always less than or equal to the minimum degree of the graph. So, let us prove this theorem. This is 19 32, if G is a simple graph, then vertex connectivity of the graph G is less than equal to the H connectivity of the graph G less than equal to delta G. This is the minimum degree of the graph G. So, we prove this theorem. It is an important theorem. K prime G is less than equal to delta G. This is a trivial part because suppose the minimum degree of let me just refer the previous example. Here the minimum degree is 3 for this graph. So, and this vertex has degree 3 also. So, if I remove these 3 edges from the graph, then the graph also become disconnected, right. But there is another way of making the graph edge disconnected. If I just remove these 2 edges, then also the graph become disconnected. Okay. So, so the edge connectivity is always less than equal to the minimum degree, because this is easy, just you pick a vertex which has minimum degree and remove all the adjacent edges to make the graph disconnected. So, that is a trivial edge cut. So, we have proved this part. Now, consider now we are going to prove this part basically that vertex connectivity is always less than equal to the edge connectivity. Consider a smallest edge cut. You understand the meaning of this edge cut. Now, the first case, case 1 is that every vertex of S is adjacent to every vertex in S complement. So, this happened that when the graph is say complete graph, when suppose I take a complete graph K4 again for illustration, A, B, C and D, and if I take okay, this is a complete graph with K 4 vertices K4. If I take my S to be say AB and S complement to be CD, then I can see that every vertex in S is adjacent to every vertex in S complement here, right. So, this will happen if the graph is complete graph, and in this case the cardinality of S complement, that is the number of edges in this cut, is equal to the cardinality of S into the cardinality of S complement, because every vertex in S is adjacent to every vertex in S complement. okay, and this number is always going to be greater than or equal to n minus 1. N is the number of vertices, because see the partition could be 1 n minus 1, S has 1 vertex, S complement has n minus 1 vertices. S can have 2 vertices and S complement will have n minus 2 vertices, and then you can see that this product is twice n minus 1. So, the minimum possible is n minus 1 when the partition is 1 n minus 1. Okay. So, this number is always greater than equal to n minus 1, and vertex connectivity is always smaller than this one, because in a graph with n vertices, if you remove n minus 1 vertex, that is the maximum you need to remove. So, the vertex connectivity is always less than n minus 1, and this is the minimum edge cut. So, this is k prime g. So, in case what I have proved is that the k prime g, the edge connectivity is greater than equal to the vertex connectivity. I hope that this is clear. Now, let me talk about the other case. It is not the case that not every vertex of S is adjacent to every vertex in S complement. So, this is this case says that there exists x, a vertex x in S and a vertex y in S complement, and these two are not adjacent, they are not an edge in the graph G. Try to think in this way. So, these are the vertices in S. Suppose these are the vertices in S, and these are vertices in S complement. It is not a bipartite graph. Okay. There could be edges between vertices in S. Suppose this is x and this is y, and there is no edge between x and y. Okay. Now, what we want is that we want to remove some of the vertices in the graph such that there is no path between x and y. So, for that purpose what I have to do is that in order to block all paths between x and y, first I will pick the neighbor of x in S complement. Okay. So, I will construct a set T. So, T consists of some vertices such that if I remove those vertices, if I remove the vertices in T, there will be no path between x and y. So, first T consists of all neighbors of x in S complement. Okay. So, it could be possible that there could be a path from first from x you come to this vertex, and then there is a path from x to y here. Okay. So, that possibility we have removed now, because we are including all these vertices in the set T, and finally, we want to remove the vertices in T from the graph. Okay. The other possibility is that there could be first from x you come to some other vertex, and from this vertex you go to y or some other vertex in S bar. Okay. So, what we will do is that we will in this part, in the part S, we remove all the vertices which has neighbor in S complement. So, these are the vertices in T first of all, and then all vertices of S minus x with neighbors in S complement. Suppose this is a vertex which has neighbor in S complement. This vertex has, suppose these are the neighbors of this vertex. This is another vertex which has neighbor in S complement. So, this is another vertex which has neighbor in S complement. So, now if you see that the way that the set T has been defined, T consists of all neighbors of x in S complement and all vertices of S minus x with neighbor in S complement. So, every xy path passes through T. Thus, T is a vertex cut, right. Now, what we do is that we want to show that okay, if you remove these vertices from the graph, there will be no path between x and y. So, you have to remove basically 6 vertices, and now what you do is that corresponds to every vertex you choose an edge. So, pick the edges from x to T intersection S complement. That means, you pick these edges, and one edge from each vertex of T intersection S to S complement. Okay, that means, you pick just one edge from each vertex in T intersection S, that is, these are the vertices in T intersection S. So, you pick one edge corresponds to every vertex, say this edge, and this yields T distinct edges. But this set of t distinct edges can't disconnect s and x and y. So, but the set of t vertices can disconnect x and y. Thus, k prime g, which is s okay. Thus, k prime g, which is the cardinality of this cart is greater than or equal to t, which is the vertex connectivity. Okay, so we have constructed a vertex cart, and clearly you can see in the previous example. So, this set of vertices can disconnect x and y, but the number of edges between s and s complement that is larger than the cardinality of t. So, and this size of this cart is the edge connectivity, which is larger than the vertex connectivity. Okay. So, what we have proved is that for any given simple graph, the vertex connectivity is larger than, is always smaller than the edge connectivity, and the edge connectivity is always smaller than the minimum degree. Thank you very much.